Hi guys, and welcome back to the video series on ODEs. Today's video we're going to talk about the technique of integrating factor, which is the fourth out of the 5 methods that we'll be learning. So what is this technique for? What types of differential equations do we use it on? For DEs, which have this form, dy dx equals to a function in x multiplied by a y equals to a function in x as well. Okay, so it's quite a specific form that we have to recognize, but when you're able to see and recognize this form, that's when you know you need to use an integrating factor in order to simplify it. Because it's added to a function in x multiplied to y, that's already quite difficult to integrate directly. And secondly, it's added to a dy dx on the left hand side, so it makes things more difficult to separate. Right? So that's when you need to use integrating factor. So when the exams come and an integrating factor question comes out, how do we apply it? Step-by-step approach is really simple. So first step is to always make sure that your coefficient of dy dx has to be 1. And next, how do we find the integrating factor, or what we call Ix? Just raise the natural base e to the power of the integral of that px function. So it means that function in x multiplied to y, we integrate that function in x with respect to x. Okay, so having that, we already have our integrating factor. Next, if you're wondering how does integrating factor work, essentially it's quite much a catalyst, which we will multiply throughout the DE in order to help it to simplify. So when we multiply the Ix throughout the DE on both left hand side, right hand side, you realize that the left hand side should be able to simplify to a product rule. So the next step usually we'll just write it is the derivative of the integrating factor multiplied to a single y. And if you work backwards, you try to differentiate this thing back using the implicit product rule and so on, should be able to get back the previous step. Alright, more in details, the question to come. Last but not least, since we have a d over dx on the left hand side and another function in x on the right hand side, we can directly integrate both sides of the equation to solve the DE. As such, your left hand side will become the plain Ix multiplied to y, and the right hand side you can integrate directly since it's a function in x. Alright, with that said, let's dive right into some sample questions for the integrating factor method. First question, solve the DE dy dx equals to 4x minus 2y. Recall the first step, it's always to get to that form for integrating factor questions, which is your dy dx, we've made sure it's a coefficient of 1, plus a function in x multiplied to y. In this case, although there's no x clearly, but that function in x will be the number 2. So it's 2 multiplied to y equals to another function in x on the right hand side. With that, we're ready to obtain our integrating factor. Ix will be equals to e raised to the power of the integral of what? Of that function multiplied to y, which is 2 dx. Which will give us an e raised to the power of 2x. And from here, after solving for our Ix, we will take this Ix, multiply it throughout. That's when the catalyst can take effect, right? That's the integrating factor. So multiply it throughout, we will have a e to x dy dx plus 2e to x y equals to 4e to x x. And the next step, we'll put it into the form of a d over dx of the integrating factor, e to x, multiplied to a y. Right hand side stays the same. And you can quite much test it out. Let's try to differentiate this implicitly. We will get 2e to x multiplied to y, differentiate the first, multiply the second, plus differentiate the second implicitly, which will give us dy dx multiplied to 2e to x. Is that not what we got in the first place here? Looks like the same thing. And that's when you know the integrating factor has worked. Now that we have reached this stage, we are able to integrate both sides of the equation in terms of x. So the left hand side, we can just remove d over dx. We will be left with e to x y equals to the integral, we can bring the 4 out, of e to x x dx. Okay, this will look like a bit of an integration by parts on the right hand side, but no issue. Follow through with that. So we will have a 4 on the outside of a big bracket, but what's inside this bracket? Let's do a quick DI table. Differentiate on the left column, integrate on the right column. What should we differentiate when we do integration by parts? Usually, first choice is to differentiate the algebra. And then since we are differentiating the x, we will integrate the other term, which is e to x. Differentiate the x one step down, one row, we get 1. One more row down, we will get 0. How about the integration column? How to integrate e to x? We will get half e to x and a quarter e to x. Recall we need to put an alternating sign for the di. And last but not least, we will crisscross. And that is how we do integration by parts. Quick run through, and we will put all these terms into the bracket. So first term, we have a positive x over 2 e to x and a negative 1 over 4 e to x. That is inside our bracket. From here, we will simplify the equation to be e to xy equals to 2x e to x minus e to x. Divide throughout by the common factor, e to x. We can get 2x minus 1. Oh, and of course, don't forget to add your c's to the end of all your integrals. Okay, and just define where c is any arbitrary constant. And having divided both sides of the equation by e to the power of 2x, the c also needs to be divided by that. So you will have the e negative 2. Negative power because it's divided by it. Okay, that is our final answer for this question. Let's take a look at the second question. Solve the dE, dy dx plus y over x equals to 1 over x. Once again, we have to get into the form for integrating factor. And it seems like they have already given it to us in the form. We just need to make it a bit clearer. So our function multiplied to y is the 1 over x. And on the right hand side also a 1 over x. Let's start by finding out integrating factor. Natural base raised to the power of the integral of 1 over x dx. The 1 over x we are referring to once again is this one, okay? The function that's multiplied to the y, which is e to the power of ln x, which will simplify to x. Multiply this integrating factor throughout the whole equation, we will get x dy dx plus y equals to 1. Okay, so having multiplied throughout by the integrating factor, we are now ready to express it as d over dx of the integrating factor multiplied to the y equals to 1. Check back, you will be able to differentiate using product rule, implicit differentiation to get from here back to where we started from. With that checked, we are able to integrate both sides with respect to x, and that leaves us with a xy equals to integral of 1 dx, which is equals to x plus c, where c is any arbitrary constant. Divide throughout to make y the subject, we will have 1 plus c over x. Let's sub the known point in. We have a known point of 1, 0. So y1 equals to 0. So 0 equals to 1 plus c over 1. C equals to negative 1. Substitute this back into the main equation. 1 minus 1 over x. And that is our final answer, which is a particular solution. And with that, from this video, hopefully you have learned more about the integrating factor, how can we use it efficiently in the exams, and the form that the equation needs to be in before we can apply the integrating factor method. Thank you for watching, and I'll see you in the next video for the Euler's method.